Okay, everyone, in this video we are going to talk a little bit about what is a derivative. Therefore, we're going to be discussing about the operation called differentiation. Okay, because we obtain derivatives through a process called differentiation. Well, basically, uh, um, general definition of the derivative is that it is a function that allows us um, to calculate the gradient or slopes, which is the same thing, uh, of any tangent line to a curve. So basically, we need to remember exactly what a tangent line is. So for example, if I draw this and I draw this line touches or crosses the curve in 2 points. That is not a tangent. That is basically called a secant line. But a tangent is a line that only touches the curve at a single point. Okay? So that is a tangent line. So basically, if we are in a mathematical context of functions, we have a function, let's say that I draw this curve. Well, basically that curve doesn't look like a curve. The derivative of this function is another function that allows me to calculate the gradient of this tangent line, sorry, that should be touching, or of this tangent line, or of this tangent line, or of this tangent line. Let's say that I make it longer. Yeah, so any of those lines can be the gradient can be calculated through a derivative. So let's start with a super simple example, which is the function x squared. Okay, it's supposed to look like a parabola with the vertex in the origin of the coordinate plane that opens upwards. Okay, and it goes infinitely. Okay, how to calculate the derivative of this function? Basically, we will need to apply something that is called the power rule, which is like basically the way of differentiating any polynomial function. We are going to discuss a little bit more in depth what are polynomials in a moment. But basically, if your function is like this, okay, a variable with a determined exponent, the derivative is going to be this expression. Yeah. Pay attention because the notation for derivatives has many versions. One of them is the notation function, the function notation with this apostrophe. But for example, let's say that you use this as a function. Well, the derivative could be either the y with an apostrophe or this notation, which is very, very, very specific to calculus. It has a meaning, but we are not going to get in depth on this here in this video. So the derivative can also be notated like this. Yeah, these in calculus are called differentials, and you can also have this notation. All of them meaning the same. Yeah, basically these and these and these and these are the same thing with the different notations. You should be able to recognize all of them. Okay, it's the same thing. But basically, we can calculate or find the derivative function by doing this, which is taking the exponent down here to multiply the variable and whatever coefficient it has, and subtracting 1 to that exponent, always when we have something like this. Okay, so let's do that for x squared. We move the 2 down to multiply, and we subtract 1 to that, which is just 2x, because 2 minus 1 is 1, and here the exponent is 1, but it's not necessary to write it. So this function is the derivative of this one. Okay, what does it what is it useful for? Well, as I said before, it allows you to calculate the gradient of tangent lines to this curve. Okay, so let's imagine that we want to calculate the gradient of the tangent line to this, but we need we need to know which point is this. So let's say that I want it to be where x is 5. So the gradient of this line, remember, rise over run, is given by this function when we replace the x for 5. So the gradient here will be 2 times 5, which is 10. That's the derivative of x squared when x is 5. But for example, if I want to calculate it when, for example, x is minus 3, negative 3, so remember, here's a tangent line, and the gradient of this line, this gradient would be 2 times negative 3, sorry for the handwriting, which is negative 6. That's it. So what happens when we have longer functions? Okay, so in this video we are only going to focus on polynomial functions. So what are polynomials? Basically, polynomials are mathematical expressions that have a specific format, which are as many terms that have a coefficient, which I am going to represent with a variable, and that variable has an exponent. But you can combine many of these terms to form polynomials. For example, the next one, but the variable has a different exponent. In general, we organize polynomials from greatest exponent to next exponent, to smaller, sorry. So basically a polynomial can look like this. Sorry. So you can have as many terms as you want. A, B, C, D are real numbers, and these exponents technically have to be integers and positive. But for differentiating, we don't need to have that condition. We can have negative exponents, we can have fractional exponents, and with that we can apply the power rule that I just talked about. So let's see, for example, another function. I am going to use g of x to make it different. G of x. Let's write a polynomial. I'm just going to make it up on the spot. So 3x to the power 5 plus 5x to the power 4 minus 4x to the power 3 plus 2x to the power 2 minus 3x plus 4. And you may say, what about that 4? That 4 doesn't have a variable. I know, but what happens is that the variable is invisible, because here the exponent is 0. Yeah, and remember that anything to the power 0 is 1. And 4 times 1 is 4. And here, remember, the exponent is invisible, but it's 1. Okay, so let's differentiate this function. Okay, so the derivative is going to be, I move this 5 to multiply here, and I subtract 1. I'm going to write the middle step like in detail, so you know what I'm doing, but you can skip this part and get to the next step. So 5 times 3x to the power 5 minus 4, that's the first term, and we do the same with all of the terms, plus 5 times 4 x to the power 4 minus 1 minus 3 times 4 x to the power 3 minus 1 plus 2 times 2 x to the power 2 minus 1 minus 1 times 3 x to the power 1 minus 1 plus 0 times 4x to the power 0 minus 1. Okay, here, especially in the last two terms, some things that are worth noting happen. But let's get simplifying this in order. Okay? So 5 times 3 is 15. Sorry for the handwriting again. 5 minus 4, 5 minus 1, excuse me. 5 minus 1 is 4. Give me a second. Sorry for the confusion some minutes ago, or seconds in the video. Plus 5 times 4 is 20. X and 4 minus 1 is 3. Minus 3 times 4 is 12. X, 3 minus 1 is 2. Plus 2 times 2 is 4. X, 2 minus 1 is 1. So I'm not going to write the exponent because it's not necessary. And you have to get used to use proper notation. And let's see what happens here. Okay? I'm going to write the whole term, and then I'm going to erase the things that are not needed. So 1 times 3 is 3. X. And 1 minus 1 is 0. But remember what we said. X to the power 0 is 1. So it basically is 3 times 1. But 3 times 1 is just 3. So this will always happen when you have a linear variable, which is when the x has the exponent 1. After differentiating, the coefficient will remain, and the variable will disappear. Okay, but what happens in the last term? Okay, 0 times 4 times x to the power 0 minus 1. It will be 0x to the power negative 1. But 0x to the power negative 1 is just 0. So basically this term disappeared. And that will always happen in any polynomial function. The constant term, which is the term that doesn't appear with a variable, will disappear after differentiating. That will always happen. Okay? I forgot this parenthesis. Yes, this is the derivative function for the original one. Okay, let's do another one, and let's wrap up this video, and you will continue with the next one. Okay, let's use another type of notation so we get used to all of them. Y equals, I don't know, maybe negative 4x to the power 5 minus 4, a simple one. So I'm going to use this notation for the derivative. So it is, I drop down the exponent to multiply, so it's negative 4 times 5 x and 5 minus 1. And remember, the constant term disappears, so it will not appear in the derivative. Let's simplify this. It's negative 20 x to the power 4. That's it. That's the derivative. So for any polynomial function, you can have that. However, some special things will happen. Like things that are not technically polynomial, but we can differentiate in the same manner. Let me give you another example using both things. So let's say that I use y equals 3x to the power 6 minus 4x to the power negative 2. This will not be a polynomial because it has a negative exponent, but we can still differentiate it, and plus 4x to the power 1/2. Actually, let's use 1/3. Now we have a fractional exponent that's also something that makes it not a polynomial, but we can differentiate it, plus 3x minus 1. Okay? Yeah? So, the derivative would be 3 times 6 times x to the power 6 minus 1 minus negative 2 times 4 x to the power negative 2 minus 1 plus 1/3 times 4 x to the power 1/3 minus 1 minus, remember, when the variable is linear, you just leave the coefficient and the constant will disappear. Okay, let's simplify that. As you can notice, I also used the other type of notation. So it's 18 x to the power 5. So what happens here? Negative 2 times 4 is negative 8. But minus a negative is just plus 8x to the power negative 3 plus 4/3, which is the product of 1/3 times 1/4. You can do that with the calculator or by hand. And 1/3 minus 1 is 2/3. Sorry, negative 2/3. And minus 3. Okay, so that's the derivative. Usually we want to do some things to these terms when we have fractional and negative exponents, but we're going to discuss that in another video. Okay, this is already the derivative. Usually you want to do a little bit more with this version, but let's wrap up for now with this.